2, right, the people will move across. Like that, right? And it will keep moving across. Right? And then these people will stay over here. Right? So that's any single population now, you can use this system. Right? Any single number. It can even be decimals, right? You can have half people, but whatever. So, so there's your system. So yeah, you created some sort of basic model which models the behavior of a travelator. Yeah, so do people have any questions about this system before I go on? No, yes? Do people understand that you can now do any single number, right? You can do, like this doesn't have to even be 2 or 1, it can be 10 and a 100, right? Let's just say it's like particles in the system. And yeah?
Just a heads up, the population vector, A should actually be the first element, not the last element. So it should actually be like for that.
Oh yeah, swap them around.
Yeah.
Yes, you're right, yeah. Because this is A, B, C, D, because I moved it across. So that means A should be the first one, because, yeah, you're right. Yeah, just a note, yeah. Okay, so now you can plug in any single number you like, right? Pretend it's not people moving, it's particles in the system, right? So it can be 10 to the power of 10 particles, or 100 to the power of 10 particles. And these systems, you can model all of the behavior of the particles in one formula. So you can map all of the behaviors of every single particle. Yes?
Yes.
Should I go on? Or any other questions and problems? No, yes, no? Should be fine then? Okay, so now I want to pose you a question. How do I reverse the system? So pretend if I'm over here, how do I actually make the system go backwards?
Times T's inverse.
Times T inverse. Yes, that's actually an interesting question. Okay. However, the inverse matrix is not a probability matrix. Okay. So my question now is, pretend so now I have a system to go forwards, right? How do I reverse the system? So obviously you can get the probabilities, right? And you can kind of like reverse your logic, right? So from A, if I say A, B, C, D. Right, originally we said that the probability of going from A to B is 100, 100, and 100, right? You can kind of just reverse it, right? So the probability of D to C is 1, right? C to B is 1, and B to A is 1, right? You can reverse the matrix, right? And you can times it on the population matrix, and it will kind of reverse everything back to the time T minus 1. Right? So yes, the inverse matrix is the answer. Well, not really. But so remember we have this formula, right? So what we want to do is So remember my question was, if I already have this, I want to find, well, not really 1, but I just want to find, okay, let's just do time 2. Yeah? I already have this now. I want to find this. Right? I don't, like, before originally I had this, the population at time 1, then I times the transition matrix, and then I get that. Right? But now I have the original population. I want to find the original, like I already have the time T plus 1. I want to have T. Right, so how am I going to do that? So someone mentioned the inverse matrix, right? So what you can do is you apply the transpose, the inverse, right? So so if you invert that, do people know inverse?
Yeah.
If not, then what happens if I'll just write it like this, okay? Obviously not allowed, I'll just write it like that. Okay, so obviously if you times one side by 1 over t, I will just say it's the inverse, but let's just say it's 1 over t, not allowed in maths. Please don't write that. But if you times one side by 1 divided by t, so you already have the probabilities, and then, so you have to divide this side by 1 divided by t, right? But then you remove this, right? So 1t divided by t is nothing, right? 1. And so now you have your, so now P1 is equal to the probability, the population matrix at time 2 divided by the transition matrix, right? Obviously you can't divide, that's why we call it the inverse matrix, right? How the hell do you divide a table, Right, so I don't even know I don't know how to divide a table. So instead, the maths people, they chose a different notation, right? Inverse, so -1, right? 2 to the power of -1 is just half, right? You just put it on a fraction and then the stuff goes in the bottom. Yeah, people got that? So, okay, cool. So the inverse, right? If you apply the inverse on one side, you have to apply the inverse on the second side, right?
Yeah.
So, yeah. And then this T times T inverse will become the identity matrix, right? The identity matrix is just all ones on the diagonal, right, and all zeros. Zeros everywhere else, right? That's the identity matrix. In other words, 1, right? In more concrete terms, it's just a 1, right? But so you don't need to write that, right? So there, you get so you kind of reverse the system. However, there is a big problem with this, right? This transition, so now we inverted the transition matrix, right? But does it verify our conditions? Remember, a transition matrix has 2 different conditions. Condition 1, all rows must add to 1, or all columns, it depends on how you write it. But all rows, the sum is 1, or, yeah, columns, it doesn't matter. And the second condition is all probabilities, right? So all the probabilities, the sum of all probabilities has equal to 1, right? And the second one is all probabilities have to be greater than or equal to 0. Those are the conditions, the 2 conditions that all probability matrices have to satisfy. Now my question is, does this inverse matrix satisfy those conditions? Yes or no? No? So, okay, no idea, okay. The answer is most likely not. Like, I'm assuming probably 80% of the time you have negative values in the transition matrix. So now the question is there any such matrix which satisfies these conditions and performs exactly the same operation as reversing the system backwards? Right? And it has to satisfy these conditions. The inverse matrix, unfortunately, does not satisfy these conditions probably 80% of the time. There will be negative values in the inverse matrix. Right? So if you have like some sort of like 0. You can verify this. Right? If you have some sort of matrix like this, right, the probability of A to A is 70%, the probability of A to B is 30%, the probability of B to A is 50 and 50, right? If you compute the inverse, you will not, well, I have to check. Actually, let me check now. Give me a second. Check. But yeah, in Python you can actually invert matrices. So the function to call inverse matrices is num
MP for Li.
Yeah, then ouch dot inverse of your matrix M. Anyways, let me just confirm. You know, I don't want to give you the wrong information. Inverse of where's the matrix format? What was 0.7, 0.3. So let's see what's the answer. Oh, oops. Oh, the answer is the inverse. The answer is 2.5. It violates the first probability, right? It's already above 1. Negative 1.5. Negative 2.5. And 3.5. Right, so that's the inverse. Clearly it violates all these conditions. Right? Well, except for the first one. The sum does equal to 1, right? 2.5 minus 1.5 is 1, and 3.5 minus 2.5 is 1. But it violates the second one, right? The probability must be greater than 0. What the hell is a negative probability? Right? So that's wrong. Right? In terms of probabilities, it's not correct somehow. So my question is there some sort of other matrix, like the reversible matrix, whatever I like to call it, right? That does exactly the same as the inverse, but it satisfies these conditions. Yes, no. So the question is, can I find any single matrix which performs the same operations, but it satisfies these conditions? That's my question. Yes, no? How many people think a yes? How many people think no? Or is like everyone confused with what's going on? Or so do people understand the question? Yeah? So I want to reverse the system, but the problem is the new probability matrix I find has negative values in it. So my question, so the question, yeah?
You can do some sort of like scaling or
Scaling? Okay, so how are we going to do scaling?
I don't know.
So we divide by the sum, like you can divide, so when you mean scaling, I think you mean like divide by the sum of the rows. But that's still negative. How are you going to fix the negative problems?
So the transition function other way around, like modeling the opposite thing, like.
But we actually have to do that. So you don't want to invert the transition matrix. Like you actually have to invert the transition matrix, right? So you have to actually model backwards. So you want to do that by hand?
I mean, like the transition function can be in the reverse direction. So like if probability from B to A to B
Correct.
is 1.
You want to reverse everything.
Yes. Other way around.
If we have 100 locations, how are we going to invert it? We can't do it by hand. And we can't program rules to do it. So my question is, you're correct. That's what we're trying to do. But can we actually find some sort of matrix which does that? Using some sort of maths?
Yes, we should.
Yes, you can answer.
So, what does like going backwards mean? So, in this matrix, right, going from A to A is the probability of the right? So,
Yes.
when you say go backwards, do you mean you're reversing the going from A to A, or like, do you mean like go from, well, I mean, so let's just kind of A to B, right? So, A to B is 0.3% or 30%.
Correct.
So, if you want to reverse it, do you mean go from B to A 30%, or do you mean just
No, the whole population. So if I have some sort of population, 1, 2, 3, and 0, and then time 2 is 3, 2, 1, I want to just have the same population matrix. I don't want to reverse the probabilities. But okay, you're right. When you reverse the probabilities, you can do that, but then your question was, do you want the probabilities to be reversed, or do you want the population, like the sum? So the sum. So you actually have to scale the sum. So that's what you're talking about scaling. So you have to actually scale your probabilities. So if your probability from moving from this point to this point is 20%, I don't want it to be 80% backwards. I actually want it to be some sort of other number which allows you to move from this place to the other. Because remember, it's not just, you're not just going from A to A, right? You also have to consider A to B, to C, right? To D, and blah, blah, like everything, right? So in fact, when you compute it, the probability will not be 1 minus. It won't be 1 minus. You can verify that as well. Because the inverse failed, so it's not 1 minus. But yeah, not the actual probabilities, the population. So the question is, can we actually find a matrix which allows you to do this sort of inversion, but not really inversion, it's not really, but I just want to find the population, just reverse it back to the original, so 1 minus times that. So, yes, no. So the question is there one or is there not one? Okay, correct, there is one. Actually, but yeah, this was one of the questions that I was trying to ask. And so, where did it go? Yeah. There is a formula, in fact. I was actually trying to accomplish it. But anyways, there is a formula. However, there is a slight condition. Remember I said that you have to find, remember the question was that I want to find some sort of, so remember P2 is P1 times the Did I do alright? Okay, yeah. Okay, so P2 is equal to P1 times the transition matrix. My question was find this, right? So my question was actually to find P2 times some inverse, some sort of thing which equals to P1, right? I want to find some sort of, I don't know, R, whatever, for the reverse matrix, right? R, right, is equal to P1. And then you can also apply like all the problem. At any single time step, you can reverse everything. Right? You can reverse like 10 times, 100 times, how many times you like. There is a slight condition. There is actually no exact formula. Because you actually have to know both time T1. You have to know both of the populations, one step before and one step after. You have to know that. If you don't know, if you just know one time, you won't actually get a matrix. You have to use the inverse. But as you can see, the inverse is incorrect, right? There's negative probabilities. So the formula is, where is it? The reverse matrix is equal to transition matrix. Right, this is divide, not inverse. Times the original probability. So remember I said you have to have at least 2 points. Element multiplied by composition. Well, I will just say element multiplier. And so that's the identity. Oh, just write it. Divided by E times 2. Element multiplication times the number of. I'll tell you what I mean later. And transpose. That's the reverse probability matrix. So what these means are, this is the original transition matrix, right? So your negative 0.7, 0.3, 0.5, and 0.5, right? This is your population at time 1, right? You need to know that at least in order to do the reversal. So this is your past population. This is your identity. Remember the identity is just ones, everything ones, and then zeros everywhere else. Right? So like 1, 1, 1, 1, 1, 1, 1, zero, big zeros everywhere else. Right? That's your identity matrix. Divide, so this is element-wise divide. It's not inverse. So element-wise divide means if I want to do 2, 1, 2, 2, right? Element-wise divide by 1, 1, 1, 2, right? You just divide element-wise. So 2 divided by 1 is 2, right? 1 divided by 1 is 1, 2 divided by 1 is 2, 2 divided by 2 is 1. Right? It's just every single element you divide. Right? This is your population at time 2, and this is your, not your identity matrix. This is a matrix of all ones, right? Not the Jacobian, but this is your matrix of all ones. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? All ones. And then using this, you can find the reverse probability matrix of your whole of your probabilities.
What this formula is called?
There's no formula name for it. It's just, so this was so this is the question I had to ask about it, and so I kind of like derived one. I actually don't know what it's called. Yes.
So it says like for any time, so you can find out for any time. So
Yes.
you need to have at least information of 2 times.
Correct. You need to have at least information of 2 times.
After that you can
Do whatever way you like. If you only have one information, then that's why the inverse fails, because it doesn't know like
Because that's
how
what
it
you were
works.
saying before and after, so I think that would be confusing. So the
Ah.
main thing is that we need to have 2 times the
Correct.
information to start with.
Correct, at least 2 times. However, now if you have this formula, the question is like if you just want to have if you don't want to have P1, what are we going to do? So you can kind of like solve this matrix. You can kind of do. Anyways, I haven't actually tried that, but if you can solve just for P2, and if you manage to solve it, you will get an equation without any time step. But that's probably not going to work. But yes, this is the reverse matrix. So if you want to verify, I'm actually not going to do that. But I can verify that in fact you will have any single matrix which does not have negative values. Right? I don't know exactly what's the when you do this, what happens, but I'll give you. We'll just get another. I'll give you an example. So now the question is, why the hell do we even need to know that? Right? What's the whole point? Right? So pretend if you have some sort of virus moving within a system. right? And you want to model like people going to work, right? So if you have, so we know that like if you're in Sydney, you want to go from Parramatta to Sydney, right? Or like North Sydney goes to Sydney, right? People when you go to work in the peak hours, you have some sort of probability of going from Parramatta to Sydney, right? As working, because you have to go to there to work. But then remember, when you go home, you have to go back, right? Are you just going to compute all the probabilities again, backwards? So instead, you can reuse the reverse matrix, and you want to reverse the whole process. That's what it's used for. You want to model the peak hour time at the morning and in the evening. That's what it's used for. An example.
Excuse me.
Yep.
If you already know P1, what's the point about computing P1?
No. So we know P1 and
For
P2.
timestamp greater than 3.
So
Yeah.
okay, I'll show you what. Okay, I'll give you an example. Okay. Let's just say we have 3 locations, right? So we already know the transition matrix. We know that approximately. Okay, let's just say this is Parramatta, the city, and this is UNSW, right? So most likely, if you want to go from Parramatta to UNSW, you actually have to go through the city, and then you go to UNSW, right? This is the morning time. Also, some people go from the city to Parramatta approximately, right? Very few people go from Parramatta to UNSW directly, right? You have to go through the city approximately, and very few people go, right? And some people in the morning, they don't really go back to the city because this is university time, right? So if you compute like the probability, probably, I'm not going to exactly write the probabilities, let's just make them up. The probability of going from Parramatta to the city is like 60% or something. Oh wait, no, there's one more probability I forgot. There's also the probability of people staying at home, right? And staying in the uni, so if you live in the uni and staying in the city. Right, so look something like that. The probability of staying in Parramatta is probably like 10%, I don't know, like 50%. Anyways, you just fill the probabilities out, you'll have to find it. So once we have a probability matrix, so you have the transition matrix T, right? And you have the original probability P1, right? You can work out P2, right? This is correct, yeah? Okay, now, your question was, if we already know this, what's the point of going backwards? Right, what's the whole point? Okay, so remember, if I go from Parramatta to the city to UNSW, right? On the way around, what happens does something happen? You know some people die, right? In car crashes, or like have heart attacks, and a virus spreads, right? During those time frames, are they going to come back to the original place? Because, are they? So someone dies in UNSW, for example, this is not a very good point. Are they going to return back to Parramatta if they die? So, how are we going to model that then? If someone died? Are you going to revert all the probabilities inside, have to compute it all again?
So that P1 is original P1 and that P1 is the new P1.
Correct, so the original, so the new one. So you understand like people died or whatever and some other crap.
Sorry, so mathematically, what are you saying is you need to compute it because you need to preserve the principle that the sum of a row is 1, for example.
Correct, and all the probabilities must be positive. Because with this, now you can do as many backwards you like. You can do, because when you do inverse and you compute like the power to some inverse, right, the negatives will just get bigger and bigger. So that's not what we want. So that's why, yes, we want to preserve the fact that all the rows must add to 1 and all the probabilities must be greater than or equal to 0. Yeah. Okay, one more thing and then we can stop. So, now the question is this actually useful? So not the reverse, we're going back to the original. So that was just extra stuff. Now the question is there actually a point in doing all of this Markov system crap and whatever stuff and blah? In fact, there is. For example, let's just do another system. Now let's talk about physics, for example. Okay? So, right, pretend this is some sort of Oh yeah, you can do Gaussian. Let's just say this is the distribution of some sort of particles. Okay, the distribution of particles. Mainly, it's in the middle. Okay, so let's say that I freeze the system. Okay, this is paused. Okay, so when I play it, what happens? What do you think will happen? Let's say that this is on a high, like some sort of like plane, right? And I'm holding a ball. What will happen to the system if I press play? Like just say it's particles, right? So what will happen is probably these particles will spread down, right? It will look something like that, right? At time 1, and then it'll probably look like that, right? Pretend these are boundaries, right? Pretend it's in a box. These particles will bounce on the box, right? Probably look like that, right? And then when it bounces, it will move back, right? Because it has to bounce across the sides of the box. Assume that all energy is conserved, so nothing, it will just continue, like forever keep going. Well, that's not really true, not energy conserved. Just pretend there's infinite energy. But as you can see, this is your system, right? It's extremely complicated, right? How are we going to model this behavior? Yes, you can use Markov Systems. So an example, so if you just assume that the probability is all even, so everything is uniform. Pretend that this was A, right? This was B. Let's just draw a map. Show an example. Oh, no, wait. So, yeah, okay. So this is your starting point, right? In the middle. Right? This is where the largest density is, right? So if you assume there's some sort of big, like all of the particles are here, right? So now let's say that the approximate probability of moving from here to here, right? Because it's regional, it moves regionally, right? But remember, all of these move this way, right? The particles will move in all directions, but I'm going to assume at equal probabilities, okay? Obviously not, but let's just assume that, right? And remember, some of it will stay in the original position, right? Some of the particles won't actually move across. So now, how many squares are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so I'm just going to assign 1, 9 probabilities. Obviously, this is not correct. I'm just going to assign it for now. So the probability of moving from here to this square or this area is 1, 9. And everywhere is 1, 9. Right? Yes? Do people get that? So just assume, just divide it by the number of squares around you. Okay? So I'm not going to, it's actually not correct, but for now, so obviously most of them will probably stay in the middle. So probably like 1/2, and then the other half will distribute it around. But I'm just going to assume 1, 9. Right? So, but now the question is, if I'm over here, what's the probability of moving from here to here? Right? If you're over here, you also need to move. Right? So what is the probability of those? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. So it's also 1, 9. So if you're over here, the probabilities of moving outwards are all 1/9 as well. And over here, right? Everything over here is all 1/9. Correct? Yes? Because if I'm over here, you have 9 different ways you can move. Right? So it's all 1/9. However, if you're over here, the boundaries of the box, you can only move up, right? This way, this way, this way, and this way, right? And you stay. So how many boxes are there? 6, right? So the probability is 1/6. And if you're over here, it's also 1/6. And if you're over here, it's 1/4, right? Because there's only 4 boxes. And yourself. Right, so now we have actually computed the probabilities of an approximate particle moving in the system. So if you write all the probabilities down, so if you consider each of these positions as A, B, C, D, E, F, G, you know, blah, 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 you have a gigantic matrix of A all the way to the last one. I said this was like, I don't know, Z, right, Z. You have all of them, and you have another matrix, A all the way to Z, right? And the probability of moving from A to A is using your stuff. You just fill it all in, right? A is here, right? A to A will be 1/4, right? A to B, so that's B, will be also 1/4, right? A to C is 0, right? You can't move from here to here. And then 0, 0, 0, 0, 0, 0. Oh, wait, sorry. Don't forget A, B, C, D, E, F, right? So if there's an F, it's 1/4. right? And G is also 1/4. Anyway, you can see you have to fill this big fat matrix up, and this is a transition matrix. So yeah, in physics, people use this for particle simulations. Well, at a much smaller scale, right? You can't just, this is a large scale. If you reduce it down to like a very, 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 very small scale, then your matrix will get gigantic. And so there's other methods you can use to not have this fat matrix, because it's way too big. It's computationally very expensive. But that's one application. Another application, right, if you realized, remember I was talking about virus spreading? Right, so if I start from some sort of population center and another population center, right, remember people can move around, right? So you have to consider the probability of people walking from A to B, right? This is walking. You have to consider that, right? But also people can take a car, right? So what is the probability of people going from a car? So you have to consider that. You also have to consider bus, right? And train, and airline, right? And water ferries and stuff, right? And so on, right? You have to consider all of these movement behaviors, and then you compute your probabilities. And also you have to consider births, right? People, new births, deaths, and so on. So using a transition matrix, you can compute all of these probabilities. You store it in some sort of matrix, and then you can compute how a virus spreads in a population. Any questions? So that's just an examples of what you can do. I'm going to talk more about it later, but yeah. Any questions? No? Just, yeah, I think it's the end. Thanks.
Hey, thank you.
Yeah.